Anastasia, can you also confirm that you can see my presentation?
Yes, your presentation is okay.
Great, thank you. So, hello everyone, and welcome to this first webinar of a series of webinars of the PrismArch project. My name is Konstantinos Sfikas, and I am a PhD student at the Institute of Digital Games at the University of Malta. And this webinar is a presentation of a number of AI innovations applied to the field of architecture and engineering in the context of PrismArch. But before moving to the actual AI aspects, let's take a short tour of what PrismArch is about. So in the following few slides, I will quickly go over the motivations and challenges behind PrismArch, its main functionality, as well as the list of partners that have made all that possible so far. So the main motivation for PrismArch was that there are a number of persistent problems waiting to be solved and opportunities to be grasped. For example, all of that in the field of the AEC industry. For example, the issue of badly informed decisions is a common phenomenon in that industry, spawning from insufficient perception of the impact of certain choices during the design processes. On the other hand, the AEC industry is characterized by the phenomenon of parallel worlds, especially in large-scale architectural projects. They are characterized by a very high complexity, where several disciplines coexist with different perspectives on the same problem. And the key to a good cross-disciplinary cooperation lies at the intersection of those disciplines and their operations. And finally, the VR technologies and the benefits of immersiveness are yet to be harvested in that industry, and that was a very important factor of motivation behind PrismArch. Now, in order to address those problems and to grasp those opportunities, there are a number of serious challenges that PrismArch attempts to deal with. The first one is that of collaboration between different disciplines within a singular design space. So a VR platform that can host different disciplines and that can provide the basic operations for those disciplines to operate and collaborate day by day. The second challenge is that of interconnection with existing software tools. Of course, PrismArch does not start from scratch. It attempts to take advantage of existing technologies and interconnect with them. For example, this may include data exchange between software such as Revit, Rhino, SAP, and others through the Unreal platform. And furthermore, there is a need for online collaboration through a system that can offer version handling and user access control. Finally, there is also a need for data logging so as to be able to trace back the reasoning and the decision-making process within complex projects that span potentially many years. So PrismArch attempts to respond to those challenges by bringing together a number of different technologies. First of all, the core application of PrismArch is built within the Unreal Engine so as to be able to provide a cutting-edge VR environment. Then the aspects of user access control and version handling of drawings and other relevant assets are handled by the Speckle database. AI assistance is used to enhance certain processes of decision-making for all involved disciplines, especially focused towards the initial stages of design where exploratory design processes take place. And finally, all of those parts have to come together in a unified collaborative VR space. So PrismArch brings together partners from different perspectives, including research institutions and the industry. The academic partners include the Center of Research and Technology Hellas, who are coordinating the project, as well as ETH Zurich and the University of Malta. From the AEC industry, we have architects from Zaha Hadid VR Group, structural engineers from AKT, and MEP engineers from Speckle. And finally, Mindesk is the software development partner specializing in VR and CAD applications. Now, before we move on, let me introduce the core team from the University of Malta. This includes Professor Georgios Giannakakis and Dr. Antonios Liapis, myself, and Anastasis Giannakakis. Now, Georgios and Antonios are experts in certain fields of AI that are very relevant to this project. I am in the process of attempting to also become an expert, although my background is also in architecture. And of course, Anastasis is a partner architect whose input was very valuable in this project for obvious reasons. Now, the actual subject of this webinar, which is is the application of certain AI methodologies to the process of content creation of different disciplines of the AEC industry. Now, the main AI methodologies which the University of Malta brought to the project are quality diversity and designer modeling. So in the following slides, I will attempt to explain what those methods are and how they can be applied to design problems in general before we go to the actual implementation of those techniques within Prisma. Now, quality diversity is a form of artificial evolution that focuses on the generation of good and diverse solutions. Now, due to its mode of operation, quality diversity is especially relevant for design-related problems, as it can help the designer to illuminate the solution space and thus expand their understanding and intuition about the design problem. But in order to better understand what this all means, it is important to take a small step back and discuss a little bit about evolutionary computation in general. So, evolutionary computation is inspired by the natural process of biological evolution, in which species tend to adapt to their environment. Now, artificial evolution is an abstract algorithmic process that treats solutions to numeric problems as if they were living organisms competing with each other. Now, there is a large number of algorithmic variations out there. However, most of them share some steps that you can see in this diagram. Namely, they begin by generating a population of random solutions initially, and then they repeat a process of selection, mutation, evaluation, and replacement. And by repeating those steps over and over again, the population of solutions tends to become better over time, converging to some optimum fitness. Now, because this process is very abstract, it can be applied to many different types of problems, as long as they can somehow be represented numerically and evaluated. So in the following slides, we will see some example applications of this concept. For example, here we can see how a form of interactive evolution, interactive means between the user and the algorithm, has been used for the generation of abstract images. It is important to note that those images have been generated from scratch, based only on the interaction, and not based on some pre-existing data. And that is in contrast to other methods that are, for example, machine learning that is based on data. In another example here, we can see how evolution has been used to automatically generate board games. One of which is called Yavalath, is also commercially available. And finally, here we can see an example of evolutionary computation applied to a case study of architectural design, where the goal was to optimize the structure's exposure to sunlight. An important side note is that this project was executed using commercially available tools, such as Rhinoceros and certain optimization plugins. So this is just to point out that artificial evolution is accessible through very popular tools and can be applied to design problems easily. Now, based on the examples that I showcased, I suppose that it became apparent that evolutionary computation can be applicable to a vast range of problems. However, as any method, it has some benefits and some drawbacks. Its main benefits is that it is let's say, its generality. It is applicable to many problems. And another one is that there is no need for pre-existing data, in contrast to machine learning methods. However, its main drawback is that it is susceptible to convergence to local optima. This means that the algorithm may, in simple words, may get stuck to some solution and not be able to discover better solutions. Another problem is that the generated solutions may tend to be similar with each other. And finally, evolution can be computationally expensive depending on the problem. Now, quality diversity that we mentioned earlier was introduced primarily as a response to one of the main drawbacks of evolution, which is the convergence to local optima. And what it does is that it attacks this problem by focusing on both fitness and diversity of the generated solutions, and thus gaining much higher probabilities of escaping those local optima. Now, another positive side effect of this approach, which we really care about, is that the generated results also illuminate the solution space and thus provide intuition to the designers about their problem at hand. Now, in this diagram, we can see the main operation of map elites, which is one of the most well-researched algorithms in the field of quality diversity. Now, as you may notice, the algorithm shares some similarities with classic evolution that we saw before. And those are the steps of selection, mutation, and evaluation. However, the main difference of this algorithm to classic evolution is that it is not only based on fitness, but it also introduces a number of perpendicular features, characterizations of the generated solutions, which help us make sure that the population will include examples that are different. So during the algorithm's operation, what is happening is that the solutions both expand and become better. So we have more and more solutions which tend to become all the more different as generations progress. Now, in order to visually grasp what that means, here we have a simplistic example of maze generation for games. And as you can see in this archive, we have a variety of mazes. On if we go towards the right, the mazes are more twisted, while if we go towards the left, they are more they include more straight corridors. And in this case, fitness has to do with the length of the solution. So here at the bottom right, we have a solution with high fitness, while on the bottom left, we have a solution with low fitness because it's a small route to get to the exit. Of course, except for those toy examples, MapElites has also been used for urban design. In this case study, the researchers generated alternative designs for 2 regions in Boston, Massachusetts, and they examined features such as wind comfort, danger due based on weather, and the ratio of open space. And they performed the simulations, the necessary simulations, by using a surrogate model for them to be faster. Moving on, in this example, we can see how MapElites has been used to explore the design space of this weird type of vehicle. This is a type of, it's called a velomobile, and of course, aerodynamics was the main problem here. It is the axis of fitness, but various other geometric features were used as diversification features. So, yes, and you can find the relevant paper by following the link down here. And to conclude with those examples, here's a preview of how we used quality diversity, actually a variation of the MapElites algorithm in the context of PrismArch in order to explore structural optimization. Moving on, let's take a look at the second methodology that we bring to PrismArch, which is that of designer modeling. Now, designer modeling is actually the application of machine learning to capturing the preferences or the behavior of a designer. Designer models can be trained in many ways. In our case, we're training them based on user selections, during which the designers explicitly express their preferences between some provided alternatives. And after obtaining a designer model, one can use it for a personalized recommender system, which can affect evolution in various ways. So let's take a look at this process in a bit more detail. Here we can see a hypothetical scenario where the designer is presented with a list of generated options, each of which can be characterized by a set of measurable features, which we refer to as a feature vector. And let's suppose that the designer makes a selection based on their own subjective criteria. The next step is that based on the designer selection, we generate a small data set of pairwise comparisons, and then we use a technique called preference learning in order to train, in order to adjust, let's say, a linear model. Now, after repeating this process a few times, the model tends to be able to predict what the designer would select for new examples of design variations. And this is very important because once we have such a model, we can incorporate it within the evolutionary algorithm and thus generate examples that are relevant to the designer themselves. So after this short theoretical introduction to the methodologies, in the following sections, we will go through the actual applications of those methods within PrismArch, and we will see them discipline by discipline, starting from architecture, moving on to structural engineering, and then MEP engineering. So in the so-called AI tool for architecture that we developed in collaboration with many partners from PrismArch is actually based on it refers to the initial stages of design where the architects have defined design specification and they want to start exploring different geometric variations of architectural layouts that satisfy those this abstract description of the. It can be a house, it can be whatever architectural space. Now, the core idea is that we want the designer to be presented with few alternatives, which is in contrast to what MapElite does on the back end. So what we're doing is that we're selecting a small region of the feature space, and we are presenting some examples from within that region. Now, the designer can select one of the alternatives and examine its characteristics. And if they prefer that solution over the others, they ask the algorithm to provide them similar alternatives, let's say. So they move towards one direction through the feature space. Now, as soon as they make a selection, as we saw before, the designer model on the back end is being updated. So the algorithm now tries to generate solutions based on the previous selection of the designer. And as this process moves on, the designer is continuously expressing their preference, and the algorithm is continuously learning and adapting based on the designer's selections. Now, having given this kind of abstract presentation of what our tool is supposed to do, let's now take a look at how it was implemented actually within PrismArch. So the first step that the designer has to do is to define the design specification, which consists of a set of space units. They can be interior spaces, they can be exterior spaces, as well as the connection between them to generate this abstract graph that you can see here. And then they combine all those into let's say, a single graph, which they can upload to Speckle, so that then they can use this design specification in the VR platform. So in the VR platform, the first step is to download the design specification, define the algorithm, a few algorithm settings, including some behavioral characterizations, which is the mode of differentiation between solutions. And after all of that is in place, the designer starts the interactive design session that I described before. And here we can see a short video that shows the actual application. As you can see, the designer can inspect the generated results. Those tend to be kind of abstract here at the beginning. You see the geometries are kind of irregular, but as the designer selects the ones they prefer, they may tend towards more orthogonal solutions. Also, they can inspect the measurable geometric features, as you can see here. Those include various forms of compactness, orthogonalities, the precision, area precision based on the connectivity diagram. And as soon as they decide which one they prefer, they let the algorithm know. And as you will see in a few seconds, now the designer model is being updated on the background, and the QT algorithm will generate new design alternatives that are different from each other, but relatively similar to the previous selection. This process can go on for as long as the designer wishes to. And at any point, the designer can select to upload one of those generated solutions to Speckle in order to share it with others, or to edit it with some other software, for example. Yes, that was it. So, to conclude with the AI tool for architecture, we have managed to put together an AI-driven design suggestion system in VR. In order to support that, we had to create an innovative algorithmic approach which brings together quality, diversity, and designer modeling within the field of architectural design. And also, we implemented interconnection with Speckle to share data with collaborators. Moving on, the next chapter is the AI tool, the application of the AI methodologies for the field of structural engineering. In this case, we have two different examples. The one refers to the process of designing the so-called stick models, which is a typical approach of structural engineers, especially during the initial stages of design. And the other one is focused on optimizing parametric surface models. I will be starting with the first part, presenting the tool we made for the optimization of stick models. And then Edoardo Tibuzzi from AKT will be presenting the other two. So let me move on. So before we go into the actual application, I would like to point out that in order to apply map-elites to engineering problems, we had to invent a form that applies to constraint problems. So, for example, many engineering problems are characterized by separating solutions to either feasible or infeasible. So what this variation of map elites does is that it treats the infeasible solutions separately than the feasible ones. And so on the infeasible archive on the left, the goal is for them to tend to be feasible, while on the right we have the actual fitness, which I will describe later on. So in this case, the tool is implemented within the Rhino and Grasshopper environment. It's at least its main operation. We are using the Caramba 3D parametric engineering software in order to perform the simulations, the structural simulations. However, on top of all that, we implemented a unique system that allows the user to both control and inspect the operation of the FI map elites algorithm, which we will see right now. So as I said, the first step is that the designer has to manually define some structural elements. They actually define the problem at hand. And then those are converted into a Caramba structural model, which will be evolved into variations. This happens through a custom Grasshopper script. And then as soon as everything is placed, the algorithm's control panel is exposed to the designer. Now, some very important parameters that we can see here are the available fitness functions. Here, for example, the designer can select between mass minimization or energy minimization, which are two typical goals for structural engineering. And on the other hand, they have available a number of features that they can select for differentiation. Those include the percentage of used elements, the percentage of specific type of elements, or alternatively, they can use a pre-trained designer model as one of those features. So essentially, the algorithm then will generate, on the one axis, it will differentiate solutions based on its preconception of what the designer would like to see. So it's important to point out that in this case, the designer model was not used as fitness, as in the previous case of architecture. And this is because in the engineering disciplines, fitness is always something very precise and predefined. So it doesn't make sense to evolve structures mainly considering the designer's taste. This is a secondary dimension. Thus, this is the reason why we use the designer model in this fashion. So, and here we can see a small example of some variations generated from this tool. So now I would like to ask whether Edoardo is.
Yes, hi, Kostas. I'm just gonna try to share my. Can I share my side of the screen?
Yes, one moment.
Thank you.
All right, now you can share.
Great. Now, you should be seeing.
Yes, we can see your browser. Yes.
Great, and I'm just gonna get the slideshow. Right. So basically, when we move, the idea was to try to move to also an additional approach. Obviously, as Kostas was mentioning, one side of things is going from the 2D analysis frame models to and also explore maybe a larger 3D space. Obviously, the AEC playground, as you can see in this slide, is quite varied, and so you know, to provide a platform that kind of trying to cover different solution for us was key of exploring maybe also like a more like a topology driven approach and so obviously in our experience we have delivered several complex high-end projects, and so we actually decided to kind of focus also on the analysis of free-form structural shells, which kind of provide us to a set of different problems. So I think, the main difference in this sort of system, this shape-driven approach, kind of needs to work as a set of discrete control variables that can allow us to shape and sculpt the forms, and obviously using continuous surfaces in this case. So kind of one of the approaches that in the industry is taken forward is to use a description of the system with a low polymesh and then subdivide it as a Catmull-Clark algorithm, and that allows us to then set up the parameters that we want to vary within the closed system, and then obviously get out some sort of an idea of fitness of the system that sort of gives the designer a space of decision and allows a designer to take a few obviously decision forward. So what we kind of this is a process that is not necessarily new in the design space, but what we have done in PrismArch is actually embedding in the platform design and leveraging on AI models to give us, a set of suggestion and recommendation through the designer. So the workflow is based on, starting from a base shape that and define the variability and the structural properties of the system. Then the second step is to mutate the shape and sort of assess a large set of variable and a large set of responses. And then obviously through the result evaluate and allow the AI to give us an idea of the fitness of the system using the similar algorithms to kind of establish the system. So in order to do that, we also had to kind of define different parameters, to kind of allow the system to be evaluated. So constraints and variation parameters, but also modeling parameters that allowed us to describe the system itself. And then we started with, evaluating in the example different kind of solutions. So the first one that we have assessed, it was a simple square-based subdivided system, 9 patches and 16 points. So the algorithm will vary the height of each point in order to optimize the shape. Obviously, this is kind of inspired on form finding examples, and each point is given basically a variability in the x direction from 0 to phi, which is represented by the green arrows. The structure is then therefore analyzed as a structure shell with pin supports, and then a classification is based on diversity set up to kind of focus on 2 target areas, in this case, the center point and the arches. So basically the algorithm setting are defined according to the system that we want to define, and basically the fitness is analyzed in terms of difference on height and average height. So in this way, we are able to kind of evaluate several different variation of the system, and also identify like the boundary conditions, so the best solutions, and also the non-applicable solutions in terms of the whole design space. So that was the sort of first example. Then we moved on with a square-based surface and XY fixity, so a similar example, and just to assess a different variability. And again, you can see from the plot, the aim here is to give the designer and the user a very, very quick assessment and a very sort of a direction to kind of evolve the actual design. And finally, we also experimented with geometry constraints. So we kind of change a constraint, moving from a square constraint system to a circular constraint. So again, you can see the variability and the kind of what you would actually expect, actually, that probably the best fit system is one that kind of takes the form of the dome, but again, the designer in the PrismArch environment will have to kind of discuss these results together with the relative AEC partners, and so the identification of the sort of the choice of the design solution will be enhanced by the AI system. And then finally, obviously, because of the focus of the research in kind of testing the platform design and the intercollaborative space with more designers, we run the example on the base model that we shared throughout the whole research, which is a model defined by Zahadi architects of a residential villa. So again, we've identified for simplicity the top surface in this case, but apply the same constraints, the same process to the system, defining the variability, the support constraints, and in this case, identifying some focal point that are where let's say discussed with the architects as fundamental points to kind of maintain as as constraints. And again, here, the interesting move from the simplistic approach to a more complex defined structures, that obviously assessing a more complex surface gives us a lot more different sort of outputs, and therefore classifying the fitness in this case is slightly more complex, but we have sort of defined an approach to still give the designer a space where some of the shells were more fit than others, coloring in this case the bottom perimeter of the result, but still having the opportunity of assessing each and every solution in depth, and evaluating the different outputs in detail, as you can see in this case. Other structural studies have been undertaken throughout the research. So again, this slide was almost just to show that we haven't focused on a specific solution, but more like understanding the design processes and also the output that the AI can actually gives us in a collaborative space, and that would be, yeah, in a nutshell, the contribution in this side. So back to Kostas for the conclusions.
Thank you very much, Edoardo. Yes, as everyone can see, the input of AKT was very impressive. We were very happy to see them take the basic modules that we developed, the algorithm, and implement them and input their own expertise on top of Rhino and Grasshopper, and generate all those wonderful examples and case studies. So I will share my screen again to continue the rest of the presentation. I hope that can someone confirm if it is visible?
Yeah.
Yeah, thank you. Thank you. Okay, so yes, the conclusions for this for the AI tool for structural engineering is that we have a custom developed constrained quality diversity algorithm applied to engineering problems, and that both versions of the tool are integrated in Rhino Grasshopper, which is a very commonly used design software. Now, we believe that through these processes, we're enhancing the process of structural design exploration, especially during the initial stages of design. And finally, we provide interconnection with Speckle to ease the data sharing with collaborators. The third and final tool, let's say last but not least, is the AI tool for MEP engineering. Now, MEP engineering, in contrast to structural engineering, consists of many different types of problems. Let's say more types of problems. So in this case, based on the input from our partners from Speckle, we decided to focus on one of them, which is the design of ventilation systems. Here you can see an example of how we are treating the problem. It is essentially the design of a specific type of diagram that has to satisfy certain constraints. And the workflow that we followed is very similar to that which we saw for the first example of structural engineering. So the designer initially defines a system within Rhino, and then this system is used as the primary input to the algorithm, which then generates variations, and the feasible ones can be inspected by the designer. So here we have a feasible solution where the routes start from the starting point properly, and following the set of rules, they provide ventilation to all the outlets, as you can see here. So, as I said, the primary sketch is defined in Rhino, and then we have developed a number of components in Grasshopper that take this sketch and pre-process it before feeding into the algorithm here. Same as before, the designer can select among some features, some behavioral characterizations in order to differentiate the solutions. Here we can see the designer can select between percentage of right angle junctions, obtuse angle, or straight or leaf junctions. And then there is also a set of available fitness functions. And they can also, instead of that, use the designer model as one of the modes of differentiation of the generated solutions. Same as before, also the designer can inspect all the generated results, including the feasible and infeasible ones, and select the one they prefer to proceed with. So concluding with this tool as well, here we also have a custom developed constraint quality diversity algorithm applied to MEP engineering problems. We believe that it can enhance the process of MEP design, and we also provide interconnection with Speckle to ease the data sharing with collaborators. Now, overall, this shape summarizes, let's say, the way that our developed AI applications fit within the PrismArch's overall structure. So we have all of them being able to exchange data through the Speckle database, and all of them are providing the same type of service to the discipline that they concern. So they actually enhance the exploration of the design space. And through this structure, it is possible that there can be a proper workflow of cross-discipline collaboration. So as soon as the architects finish with a primary, let's say, sketch of a layout, they can share it with the structural engineers. They can perform their structural case studies, find alternatives, then pass the information to the MEP engineers, and so on. And this concludes the main content of our presentation. Overall, we are very happy to have contributed in this project. It has been a collaboration with AEC partners that delivered 4 applications of quality diversity with designer models in VR and in Rhino. We have already published 4 relevant research papers to top-tier conferences, and there are more scientific publications underway in collaboration with the AEC partners. And overall, we believe that we have managed to integrate AI across disciplines through respective tools and the central repository and access control system. So at this point, if you have any questions, or if someone would like to comment, we have plenty of time still. So I will temporarily stop sharing unless someone needs us to go back to a previous slide or something. Just a few comments from myself then, until someone decides they're not shy to ask a question. Overall, as you can understand, PrismArch in general has been and is a very ambitious project aiming to solve some tremendously difficult problems. And despite that, and despite the big challenges that all aspects of PrismArch had to face, we're very happy from our own perspective to have been able to apply the methodologies that we're using to a new domain for us, and to the domain of the AEC industry. And apart from the existing publications and the planned publications, we will be very happy to share the modules, the developed modules for quality diversity-driven design publicly at some point. You know, this can go hand in hand with the publications, of course. And yes, I don't know if Edoardo has something to comment on that. Yes. Yeah,
I mean, first of all, thanks for everyone who's attended today. I think what's important also to kind of highlight is obviously it's been a 2 years research, and what this been sort of shortly presented.
Edoardo, we lose you. I can't hear you. I hope it's... I don't know if it's my connection or yours. All right. I think we lost Edoardo. Let's wait a little bit in case his connection comes back. Thanks, Jolie. Okay. Go on. All right then. One last note. As you probably already know, this is not the. This is only the first of a series of webinars. So you can use this link. You can write it down. To access to find more information about the upcoming ones. All of them are very interesting. I would suggest that you give them a shot. And on this note, if there are no questions, we can conclude this meeting. I would like to thank you very much on behalf of the whole PrismArch team and the University of Malta. And we will see you on the next webinar. Bye-bye.